afternoon. We're going to get started. I'm Patricia Gruber, the president of the Peter Gruber Foundation. We'd like to thank the IAU for the opportunity to present the Peter Gruber Lecture. It is my pleasure to introduce Dr. John Mather, who will present today's Peter Gruber Lecture. Yesterday, Dr. Mather received the Gruber Cosmology Prize along with the COBE team. And today we'll learn just what COBE achieved and how the legacy of COBE is being built on to help us further understand the birth of the universe. Ladies and gentlemen, John Mather.
Good afternoon. Is this working well? Okay. Well, I'm very proud to be able to represent the COBE team here to tell you what we've been up to, how it started, and where we're going. So, again, our thanks from the whole COBE team to the Gruber Foundation and to the IAU for the recognition that we now have. And now I want to tell you what it was that we did, as much as I can tell you in 45 minutes. So if I push this little button, I'm supposed to see the next slide in a moment. Let's see if this works. There we go. I wanted to start with the beginning of how people got into this business, and there was an awful lot that was accomplished by thought alone, without the benefit of detailed hands-on measurements. And I have pictures of some of our great heroes here, just to say these people thought about what we should see before we saw it. I guess the stories of what they did are quite well known to you, but Georges Lemaitre and Albert Einstein certainly figured out that there should be a Big Bang, and George Gamow and Robert Herman and Ralph Alpher figured out that there should be a cosmic background radiation. And Rashid Sunyaev told us what the spectrum should be, even in case there were a few changes about the early universe and something happened. And Jim Peebles told us a lot about how this all would work in immense detail if there were fluctuations and variations, and talked about also what would happen if early galaxies were different from what we thought. So we have a huge number of predictions. I don't have on here Edwin Hubble's picture, because he actually went and measured, but on my next picture, I think we have some of our heroes in the cosmic background spectrum experiment business. I wanted to show you their pictures to say these people are people that I worked with, or actually in some sense competed with in one of these pictures, to get things started. So Paul Richards was my thesis advisor at Berkeley, and this is a picture of him from the days when we were starting the spectrum experiments up. We did an experiment on the ground and then one with a balloon. Mike Werner was my partner. He was a postdoc when I was a graduate student, working with Paul Richards and Charles Towns in the labs at Berkeley. David Woody was my fellow graduate student, working with me on the balloon payload that I'll show you a picture of in a bit. He is actually the one who made the payload work after I escaped from Berkeley, so that actually made the whole subject credible. Frank Lowe was a person who originated an awful lot of infrared technology, and particularly infrared detectors. He made detectors that we use in our labs. I can't remember now whether the one that we flew on our balloon payload was made by him or by us, but in those days it was a pretty different subject to make an infrared detector. We did it by hand. Herb Gush was a competitor of ours. He was building rocket experiments at the University of British Columbia, and he did awfully well and very nearly scooped the COBE. Ray Weiss, in the early days, was building balloon payloads also to measure the spectrum of the cosmic background radiation, and so he is one of the people that we were competing with when I was a graduate student. Then we became partners on the project. So my next picture should show you, let's see, did this work? Okay, people who started the COBE project up. Pat Thaddeus was my postdoctoral advisor at the Goddard Institute for Space Studies in New York. I had actually come to the conclusion after finishing my thesis project that this work was much too difficult, and I wanted to escape. I wanted to do radio astronomy, because to do all this work and all you get is one number, maybe the temperature of the background radiation, and how important is that? Anyway, Pat said one day that there was this announcement of opportunity from NASA to send in proposals, and everybody in the lab could bring their ideas forward. So I had my idea about my thesis project, which hadn't yet worked properly, but I said this is something that really would work a lot better in space. So Pat encouraged us to form a team, and so we did. So now I have pictures of our original team members. There's me with my wife, Dave Wilkinson, who Pat said I should call up with his wife Eunice, Mike Hauser with his wife Deanna, Ray Weiss at MIT, and I don't have his wife's picture, but at any rate, we were the initial group. We drew in more people from Goddard and MIT, and we wrote a proposal. Now, while I was completely unaware of this, but there were also teams at Berkeley and Jet Propulsion Lab, and here's a picture of George Smoot, who was working with Louis Alvarez to send in the proposal. And here also are Sam Gulkas and Mike Jansen with their spouses. They were working on another competing proposal from Jet Propulsion Laboratory. So both the Berkeley and JPL proposals were for anisotropy experiments to measure the hot and cold spots in the Big Bang. Anyway, this was the group that started up working on the project. And then eventually, after we were started by selection from NASA headquarters, let's see if we can get the next slide here. We added more team members. Come on for the next slide, please. Okay, we added team members over the next several years. Here are some of our key members. Chuck Bennett with his spouse, Renee. Nancy Vargas with her husband, Al. Ed Cheng, I don't have a picture of his spouse here, but all of these people made tremendous difference to us. Ellie Dweck, one of our theorists on our team, his spouse. Tom Kelsall, who also worked on the Hubble quite a bit. Phil Lubin with Georgianne, all joined our team, and we have more. We totaled up 19. This is in our next slide. Let's see if we can make this come up. Okay, the rest of our science working group, Steve Meyer, Harvey Mosley, Tom Murdoch, Rick Schaefer, Bob Silverberg, and Ned Wright. So I have their spouses' names here because it was very important to us that our spouses put up with us and helped us and made this a possibility. So our thanks to all of our family as well as to the Gruber Foundation for getting this started. Now on the next pictures, now I'm going to show you what it was that we actually did. Let's see, here are the science team members, a short version of the history. I told you we were proposing in 1974. Headquarters chose 6 of us to be forming a mission definition science team in 1976. So these members came from all 3 of the teams, and we were to figure out what to do. This was from a day when a proposal was thin, and people just said, we have a good idea. And these days, when you write a proposal, if you want to win, it has to be an inch or 2 thick. This is the old days when you had a team selected to then figure out what to do. Ray Weiss was elected as Science Working Group Chair. I was appointed as a project scientist. Eventually, Nancy Vargas came from headquarters to join me at Goddard and worked with me as my deputy. Mike Hauser was the principal investigator for the diffuse infrared background experiment with Tom Kelsall as deputy. George Smoot, principal investigator for the differential microwave radiometers with Chuck Bennett as deputy. Rick Schaefer was my deputy. And Ned Wright was the data team lead, so he made sure all the calculations were right. Now here I want to show you a picture of our engineering team. This was taken a long time ago, shortly before launch, and these are the team members who you don't hear about, but they actually are the ones that we counted on to make amazing things happen. Just a couple of people I want to mention. Roger Matson was our project manager, and Dennis McCarthy was our deputy project manager, and they were the people that made the whole project go. And in particular, Dennis McCarthy was the one who rescued our project when it was determined that the shuttles were never going to fly from California to carry us into orbit, and we had to redesign the mission so that it could go on a Delta rocket. He found that it was possible, and he made it happen. Now, stepping back in time to what was physics like in 1970, it was a little different. This is when I started my thesis work with Paul and Mike, And in those days, we just didn't do it the same way. We had very, very different tools. Your amplifier for finding a small signal was made with vacuum tubes. The Fourier transform, the fast Fourier transform that is in the basis of so many pieces of electronics these days had just been invented. There were no pocket calculators. An advanced computer, the one that we had in our lab at Berkeley, was a PDP-11 which ran a paper tape. And so this was something which was a true accomplishment to program, and it could do Fourier transforms. Infrared detectors were made by hand. You had a little chunk of germanium, and you had some acid, and you put it in a protective hood with rubber gloves, and you soldered it and etched it and did all kinds of things to it until it could detect infrared. So I did that. Frank Lowe's company could do that, and we all depended on this very amazingly sensitive yet primitive technology. So this is a schematic of the first experiment that we tried to measure the cosmic background spectrum from Berkeley. We had heard, as Virginia showed us yesterday, that there was something the matter with the spectrum. So this was our apparatus to go find out if it was true or not. We had a cryostat on the left-hand side. You see there the detector in a cryostat that we bought from Frank Lowe. There was a Fabry-Perot interferometer with a lens, and then there was a long pipe. It was about 12 feet long pipe that led from the inside of the building to the outside of the building. And then outside was some more lenses and a chopping device with a black body to calibrate. So this was our way to see through the upper atmosphere. We had to take this up to the 12,000-foot station of White Mountain in California. So naturally enough, we said everything's okay with the cosmic background radiation, but of course from the ground you can't really tell very well because the background radiation is very faint compared to the atmospheric emissions. So in our next slide, we will show you, what will we show you? We'll show you the next slide. The next version of the project was designed by Paul Richards for the graduate students to work on. And so this is how that was supposed to be done. It's an improvement over the ground-based version because it carries its devices up above most of the atmospheric emission. And it had its own internal calibrator. So we were beginning to think about differential calibration schemes. This all was carried inside a liquid helium cryostat, which you can barely see there as the outline here. But the apparatus ran at about 1.5 degrees Kelvin, which is amazingly cold. But it was enough to make the detectors good. A superfluid helium pump actually poured liquid helium up on top of the cone antenna. This cone antenna up here was the device that said, well, we're only receiving light from the right part of the sky. So it had to be cold also. So I got my thesis out in 1974 based on the design of this apparatus and on the work that we had done on the ground. Then in physical review letters, we published the results, and that was based on the second successful flight. And that was a result which said, yeah, there's still nothing the matter out there, although it was a little tempting to think that there was more. This is Paul Richards giving the apparatus to the Air and Space Museum, which you can now go and see in Washington, D.C. So it gives you a sense this is big, but not all that big. And inside there are all kinds of astonishing things that were made in the shops in Berkeley. So here is coming now to the history of COBE. What did we do? In 1965, the cosmic background radiation was announced. Penzias and Wilson found it. Dickie Peebles, Roland Wilkinson were hunting for it at the time, and I guess this story is very well known. I told you already about the proposals that were sent in 1974, and in 1976 our team was chosen. Then I've abbreviated the entire history of COBE to say we made a lot of sausage. We did an awful lot of meetings, we built a lot of stuff. A lot of things didn't work the first time, but that's the normal condition. And in 1982, we were finally approved to build this project for flight. That was a time when we were waiting for other projects to be ready. In fact, the infrared astronomical satellite was the first big cryogenic mission in space like this. And they developed the infrared technology for cryostats and for some of the detectors that we would use. So we had to wait until they were pretty well along before people were not so terrified of having cryogenic things in space. Then we were busy building along, and then in 1986 the Challenger space shuttle exploded. All our plans had to be abandoned. The Challenger was never going to fly. There were never going to be space shuttles going up from the California launch site. So we had to redesign. And we were very fortunate that the 10,500 pounds of original design payload could be reduced down to 5,000 pounds by very careful thought, because that was just about the maximum capacity of the Delta rocket. So another 3 years passed, and we actually finished this space payload and launched it on November 18th in 1989. And it went up. It was an amazing thing to see launched from California at dawn. Terrifying as well. In just a few weeks actually later, we had our first results from the spectrum experiment, which I'll show you in a moment. The helium in the cryostat lasted for 10 months, but we could keep on running the rest of the payload. The microwave radiometers continued to work until 1994, and also so did the shorter wavelength detectors for the infrared background experiment. So here's a picture of what the satellite looks like. This is, of course, an artist concept, because if it were really a photograph, you would not be able to see the instrument package. It would be dark. The whole point of this design was that the payload would protect the instruments from the sun and the Earth. And so in this drawing, the Earth is below the payload, and the sun is shining in from the side. And the payload spins around its symmetry axis here, so as to scan the instrument lines of sight rapidly around the sky. It took about 72 seconds to make a spin. So when you watched it from the ground, on those few times we were able to see it from the ground, you'd see the solar rays flashing at you several times per minute, as each solar array would come into the line of sight where it could reflect sun down to the Earth. So this is the payload. There are 3 instruments in it up at the top. There is a cryostat in the middle that carries 2 of the instruments, the spectrum experiment and the infrared background experiment. And attached to the outside of the cryostat, around the outside of the cryostat, are 3 boxes that have microwave receivers to measure the hot and cold spots in the Big Bang. So here's a diagram of the spectrometer. This is very much similar to the one that was in our balloon payload from Berkeley. But the tremendous advance that's now possible because we're in space is we can now have an external calibrator we call the movable black calibrator up there at the top left. And that can be a black body. The ideal that's predicted can be actually placed in the horn antenna to replace the sky. So if the sky has a black body spectrum as predicted, and the calibrator does the same, then when you take a measurement, you should get no difference. So that was our strategy, to get a tremendous improvement in accuracy by flying a Big Bang simulator. That movable black calibrator is a simulator of the Big Bang in a curious kind of way. So without going into details about how this whole device works, it's a rather long, elaborate process to take the data, but this was the ideal concept for measuring the Big Bang spectrum. So in our next picture, we have, I think we have in the result. Oh no, I forgot. We have a picture of the calibrator itself. This is the flight light, the test unit device for the antenna, and there is the calibrator. In this case, you see it before it's been covered with insulation. There is metal all over the black plastic outside to make sure the temperature is all correct. And you see a little protective device, a little white piece of plastic up there that's supposed to make sure that the tip of the device is not ruined in the test program. One of the most critical things in our program was to make sure that was removed before we installed this in the spacecraft. So the next picture actually is the result that we showed to the Astronomical Society in 1990, the one for which you've heard the laudatory stories. And it was indeed based on 9 minutes of data. We had, after the course of 10 months of operation, many more data points, and a vast amount of computing was required to make sense of it all. Of course, this apparatus did not work perfectly, as hoped. On the other hand, it worked so well that we were able eventually to reduce these error bars to about 50 parts per million. So, Ali Dweck is a brilliant artist and cartoonist, and he drew us an illustration of what this means. So, The cosmic background really does come from a hot Big Bang. There is no serious alternative explanation for that. As many people realize, there was a very popular theory called the steady-state theory that was an alternative to the hot Big Bang, and it held that it was the universe was replenishing itself. But that theory really had a very hard time making a prediction that the Big Bang radiation should be such a perfect black body. So we also know from this that hardly anything happened after the first year. There could have been, in principle, elementary particles, some kind of unstable particles that we didn't know about that would decay and release energy and turn it into cosmic background radiation. Or it could have been that the Big Bang was turbulent, and that the turbulent motions that came from one part of the universe being different from another would have released energy and changed that spectrum. But that did not happen, at least not in a measurable way. So we certainly will be interested to see if there are future traces, but this was not the major thing affecting the expansion of the universe. So on our next picture, I think we're going to the next, this is the picture of the residuals. How much different is the temperature from the average? And you see that the error bars are quite small in the middle. We couldn't even plot them. About 50 parts per million on the spectrum. Now we imagine, this is an ambitious claim, that if we were to try again with a new technology that we could do about 100 times better. So far, theorists have not told us we need to do this, and we have not had to deliver on this promise, but we think it can be done. So now, changes happen. I find cartoons occasionally that illustrate the state of our universe, and we found out a lot of things we didn't know from the next experiment. So the next experiment I want to describe to you is the one that looked for the hot and cold spots in the Big Bang. Here's the diagram for how this works. There are two antennas that look at different parts of the sky that are separated by 60 degrees across the sky. And there's a little switch at the front that says, okay, first I'm going to look in one direction and then I'm going to look at the other. And this switch is flipped back and forth 100 times a second. So then this information then goes from the switch into the amplifiers and the detectors, and at the end you look to see whether the output of the receiver goes up and down 100 times a second or not. And that difference that comes out at the end is a measure of the difference in brightness between the two directions that those two antennas are looking. So this was a traditional design in the microwave receiver business, and we've been using this for many years before the COBE was proposed. But we were going to do this in space, and we were going to be able to do it better because we would be able to spin the spacecraft in every possible orientation and measure all the possible differences of brightness between two parts of the sky 60 degrees apart. So we ended up with this archive of 4 years of measurements of those differences and a computer program to put it all back together to make a map of the sky. So here's a drawing, a photograph rather, of a model of our first, in our low-frequency radiometer. What you see here are the two horn antennas, very large, pointing out 60 degrees apart. Then there are the waveguide hardwares, and there's a block in the middle here called a switch block where that 100 hertz switching device is placed. And then this is all going to get covered up and protected and stuck on the outside of the cryostat to look at the sky. So here's the result. After we've processed those hundreds of millions of observations and unscrambled them, this is a map of the sky, and these are the pink and blue blobs of the beginning of the universe. The differences that we see here are very small, apart in 100,000 of the total brightness of the sky. And with our microwave antennas, we were able to see blobs about 7 degrees across, which is pretty large. This is a pretty fuzzy map. But this was the first measurement of these primordial fluctuations. They are now thought to be representing some kind of quantum mechanical process in the early universe. So that's it. That's the beginning of the universe. It's the baby picture. The universe was about 389,000 years old when this picture was taken, because that's when the universe became transparent, according to the Big Bang theory. The early universe was opaque because it was ionized. The electrons and the protons and the helium nuclei were separated from one another, so a photon of light could only go a very short distance before it would bump into an electron. Early universe was opaque, when it became cooler at about this age of 389,000 years, it became transparent enough that the light could come to us from wherever it was at that time. And so this is a picture of that moment. So this is an illustration of the steps that the data had to go through to reach this conclusion. The original map actually does not show such all these lumps so easily. The primary effect that we see, this is a map, the top oval is a map of the entire sky, and it shows that the sky is brighter in the direction of the constellation Leo, because that's more or less the direction in which the Earth is headed through the rest of the universe. A combination of motion of the sun around the middle of the galaxy and the galaxies flying towards other galaxies produces that effect. And it's about a part in 1,000 of the speed of light that we're moving, so we get about a part in 1,000 difference in temperature between the hot direction and the average. And so then we say, well, we knew that it was supposed to be there. Although, in truth, we didn't know what the velocity was supposed to be, and there was even controversy over whether this could be properly explained. But it's now considered to be well enough explained. The middle picture here shows the effect of subtracting that effect. And the main thing that you now see is a bright red stripe across the middle of the oval, and that's the emission from our own Milky Way galaxy. It's very bright, and it's not what we were after either. It's very interesting in itself. It comes from electrons hitting each other, spiraling around the magnetic fields, and crashing into protons. But at any rate, we had to make a model of that too, and we were able to do that because we had measurements of 3 different microwave frequencies. So that's the way that we produce this map at the bottom, which is the map of the universe. Now to talk about the third instrument, which we call an experiment, because we're physicists, I suppose. The diffuse infrared background experiment, the purpose of this was to map the sky at all these wavelengths from 1.2 up to 240 microns and see what else was out there. This was something for which there was no serious prediction. We had plenty of ideas about what might have happened, but there was no way to tell them apart. So the aim was just go get the data, measure the sky, see what's out there. And we knew that there would be all kinds of things that we already knew about, from dust in our own solar system, from stars in the galaxy, from dust in the galaxy, from other galaxies. And we wanted to go find all of those things and say, well, if we take out everything that we know about, what's out there besides that? Because possibly the early universe has been filling up the universe with radiation that we would never be able to recognize except by this method. So that was the third instrument. Mike Hauser was the principal investigator. And on our next chart, see if we can get that to come. I'll back up one there. There we go. Back up another, please. I think we have a diagram. There we go. This is a diagram. This is a very small telescope. This telescope has a 20 centimeter aperture, not that big, and works at this entire huge range of wavelengths. It's buried down inside the helium cryostat, and it's very different in concept from most telescopes that you would make, because it's not intended to make a very sharp image. It's intended to make a very accurate picture of how bright is everything. So everything about this is intended to make it accurate. So in particular, there's another one of these switches that vibrates to modulate the radiation, so you can tell what part comes from outside the sky and outside the instrument and what parts from inside. Very much like what we do in the microwave business. Here's a picture of hardware. This is the test unit. Just gives you some idea that this is a very complex structure made of metal. Copper and aluminum are the main materials here. So this is a result. This is what the sky looks like. If you average the data over the whole year, at 4 different wavelengths out of the 10 that we use. Short wavelength, 3.5 microns, medium, 25 microns, long, 100 microns, and very long, 240 microns. You see the sky looks very different at these different wavelengths. At the shortest wavelength, we're showing you a lot of stars, and the galaxy is white there in the middle. At the medium wavelength here, we're seeing a bright band which is diagonal here because in this plot the the solar system, the plane of the solar system, the ecliptic plane, is tilted relative to the galactic plane, and it just happens that they intersect right in the middle of the galaxy. So that's more or less of a coincidence. Anyway, so you can see the zodiacal brightness is extraordinary. It hides almost everything else. Longer wavelengths, we see much more interesting structures here due to the dust in our own galaxy. So these are the things we saw immediately, and none of these were what we were really after. So we had to understand them completely and subtract them as best we could. So on the next picture, we show you that process and the result of that process. Here is the observed sky at long wavelengths. This is one of the color pictures where we've combined 3 wavelengths to show you the hotter things are blue and the cooler things are red in the top picture. Then when we actually make a mathematical model, we say we understand how this interplanetary dust moves around. We can subtract all that out and have a picture that doesn't have the blue streak anymore, and that's the middle picture. We still have the galactic emission, dust in our own galaxy across the middle. Then we say, okay, now we also have enough information to make a calculation of that and subtract that out. And now when you've done that, you can see this bottom picture, and that's the picture of the early universe if we got it right. Now you can tell that there are a lot of things in here that are not early universe. The Magellanic Clouds are showing up, and there's still pieces of our own galaxy showing up. So this was still pretty tricky. You cannot just say, I see the early universe here. So you have to do very, very diligent calculations to see what is the right answer. So we did that, and it took a long time, but now I'm summarizing for you here the final results of the mission in a very abbreviated fashion. We have 3 main experiments, 3 main results. The first one, the Big Bang radiation has a black body spectrum, as it should if it really comes from the Big Bang. The deviations are very small, of order 50 parts per million, and almost nothing happened after that Big Bang to convert energy from any other form into cosmic background radiation. So this is the thing that said, okay, really the steady state theory could never do this. The second result is we've seen the spatial structure. We've seen the baby picture of the universe. The spatial structure is very faint. It's only 1,000th of a percent in amplitude, and we got the map of it for a rather fuzzy map, but on angular scales of 7 degrees and larger. We were able to understand that this is now consistent with the theoretical predictions. There is something called a scale invariant theory for how bright the large blobs should be as compared to the small blobs. And so that calculation is consistent with the predictions of inflation. Now, the inflationary theory of the universe, which most people have heard of now, did not exist when we started off with this mission, and no one had any idea that it could ever be a real idea. But now that we have that theory, we're able to say, yes, the COBE measurements are consistent with that. They're also consistent with something we didn't know about before. We had a clue about dark matter, that there was a lot of it in the universe. We didn't know really yet how much. And there was a clue that maybe, or maybe not, there was the expansionary force, the Einstein lambda constant, or something like that. But I know when we started this project, prejudice was, oh, that's kind of silly. Who needs that? That's not elegant. And we thought that because astronomy was such a lovely subject that we could guess what the right answer was because it was going to be pretty. Well, not true. And the third instrument showed us that the cosmic infrared background radiation does have 2 parts. The part that's left after you subtract all of those things that I showed you in the foreground, there are 2 parts. There's a near-infrared background radiation and a far-infrared background radiation. And each of them has a brightness that's comparable to the total luminosity of all the galaxies we knew about before. So we now know that the universe has been busy producing radiation in some fashion, probably from stars and black holes, that has been converted into infrared, probably because these objects have been buried inside dust clouds, which would absorb the radiation and turn it into infrared radiation. So those are the main things that we found. Now I want to show you what's been done since and what will happen in the future. Here is the Wilkinson microwave anisotropy probe. It was built by Goddard and Princeton. Chuck Bennett was the principal investigator, and Dave Wilkinson led the Princeton team until he died, and now we've named the mission after him. So this was launched in 2001, and our next picture shows you that we have now much better data. You can see how much finer the detail is, and this is now an extraordinary accomplishment. And to hear really what they've accomplished, you need to have a long talk, because this mission has been working beautifully for several years now, and they're continuing to improve the results. But this now summarizes the sort of most surprising result. We now have a precise measurement from the geometry of the universe that's measured by those little blobs. We now can calculate how much of everything there is. Our little atoms make up 4% of the total mass energy of the universe. It's called omega baryons over there. The dark matter, which we had suspected existed and had some measurements of before, we now know that it is 23% of the total, and that there is a dark energy that causes the universe to accelerate its expansion. That's 73% of the total. So, who knew? Well, now we know very precisely. And the Wilkinson microwave anisotropy probe also measured many other things. They've measured the polarization signals of the early universe and told us that they know when some of the first galaxies started to light up, because those would affect the microwave background radiation as well. So this was something we didn't know they could do when they started. And we did expect this picture, but we did not know they could measure the time when galaxies lit up, but they did. So on the next picture, I think we have a picture of the result. This compares the results of the WMAP with the results of several other projects that are working to measure at finer spatial scales. Now this is an astronomer's picture that says large angular scales are on the left and very fine small dots are on the right, and this is a measure of how bright those dots and blobs are versus angular scale. So large on the small on the left. So large objects are on the left, small ones are on the right, and we see that the map gets smoother and smoother as you go to finer and finer scales, but the astonishing thing here is you see these giant wiggles in the plot, and those are thought to be representative of the sound waves of the early universe. And so the details of those sound waves are what enable us to calculate the geometry of the early universe and the contents of the universe with the hot and cold dark matter and the baryons. So this is not the end of this subject at all. More is coming. Here is the next mission that's coming into space, the Planck mission. It's scheduled for launch in 2008, I believe, and it should extend the WMAP results to higher frequencies, shorter wavelengths, and somewhat better angular resolution, so finer scale maps will turn up. So all those wiggles that you saw in the previous plot, way out on the right-hand side, those will be much better measured. So this is coming soon. There is yet another mission that people want to build that would come after this, called a Cosmic Background Polarization Instrument. We don't know what that would look like. A lot of scientists are thinking about it, but we hope that will come. And I think my next picture is a picture of what I'm working on now. This is the James Webb Space Telescope. It's the planned successor for the Hubble Space Telescope. It's the project of an international participation led by NASA with major contributions from European and Canadian space agencies. This is a telescope which enables us to look at infrared wavelengths. It extends and uses the cryogenic technology that have been developed for these other missions I told you about. And this is going up in about 2013. So the telescope is huge. It is 6.5 meters across, which is considerably larger than the largest rocket, which is about 5 meters across. So this is a folding telescope. You can see that it doesn't look like a round telescope. Way up here you see that there's a hexagonal primary mirror. It's a parabolic mirror. It focuses the light towards a small secondary mirror that's out on that tower. And then the light bounces into an instrument package that's behind the center of the hexagonal primary mirror. You see something that's quite different from the usual round telescope underneath, because you see a sunshade which protects the whole observatory from the sun and the Earth. We're going to put this one in deep space, the Lagrange point L2, which is about 1 million miles from here, at 1.5 million kilometers. So it's too far away for us to fix it if it goes wrong, so we're going to get it right. It's adjustable in every possible way so that the mirror can be shaped after we launch. And it will carry 4 instruments to look at near-infrared wavelengths, to make pictures with the camera, to get spectra. Could you back up for a sec, please? That's my punchline. But I did want to tell you a few more words about the telescope first. If we could back up, please. Yeah. So there are 4 instruments that include a camera, a spectrograph, a mid-infrared instrument to extend the capabilities out to the wavelengths at which human bodies and Earth-like planets will emit, and a fine guidance sensor which has actually some capabilities to help us hunt for planets as well. There are several major objectives here that we have in mind. Clearly we want to extend our cosmology. We want to go see those individual objects that lit up the first sky, the first objects that formed after the Big Bang. We want to see how galaxies like our Milky Way were assembled out of little bits, probably. We want to see how stars and planets are made, because they probably are all being made inside dust clouds where you can't see without infrared capabilities. And finally, we want to see planets, if we can. We have expectations that individual planets can be imaged, some of the bigger, brighter ones that are close by. And we certainly think that we can see planets as they go in front of their parent stars. When a planet goes in front of its parent star, the brightness will diminish a little bit. We'll say, aha, something happened. We've seen this happening already in quite a number of planets. And with the James Webb Space Telescope, we can do it a lot better and have even a hope of learning about the chemistry of the atmospheres of those planets. So now let's go to our final picture, which is our thanks to the Gruber Foundation. And this really is the caption that came out in this cartoon many years ago. We thank the Gruber Foundation very much for the recognition of our work. And I'm sure that we all appreciate tremendously what you have accomplished and made possible for us as well. Thank you very much on behalf of all of us. We do have time for questions if people like to do that. Yeah. After James Webb. Well, James Webb will last for a while. 2013 launch, 2023 end of life perhaps if we achieve our objectives. I don't know what perspective I'll be having at that point. How long will the cryogenics last? This telescope actually has an active refrigerator on it. It does not have a stored helium, so it could run forever if things don't wear out, which was a tremendous accomplishment for our team. This question there. The question is, since we now say that the age of the universe is 13.7 billion years, based on the WMAP results, how did we do that? And I think the calculation basically says we are able to calculate this expansion rate based on a tremendous amount of theory, but the physical size of those blobs, the pink and blue blobs, tell us how what's called the horizon size. They tell you how big the universe was at an earlier date, because that's the time when the universe became transparent. So we get a sample of the universe when it was 389,000 years old. And we see, well, the blobs are so big, and the size of the universe at that time is recorded in the sizes of those blobs. So from that, and from a lot of calculation, you can do this thing. It's not simple. Yes, it does. It's a separate calculation, and it's lovely that it now does agree with the measurements from receding galaxies. There was another question over here. Yes.
Would you like to tell us, please, about the density parameter of the total universe, and perhaps the shape of the universe, or perhaps the topology of the universe further, perhaps? Please, thank you.
I'm not quite sure I understand the whole meaning of the question.
Please, would you like to tell us about the density parameter, the total density parameter of the universe? I mean, the ratio of the density of, compared to the flat form of the universe.
I think, are you asking whether the universe is spatially flat?
Yeah, and perhaps further the shape of the universe. Perhaps you could tell us finite or infinite universe.
Yes, I think that the measurement says that the universe is now considered to be spatially flat, which means to say it's going to continue to expand, and its net curvature is 0 in the spatial dimensions.
Yes,
so this is a curious, not necessarily, it wasn't something we knew would be true. It's a measurement.
But the density, I think, is greater than 1, right? The density parameter. It means that the form of the universe is spherical, perhaps.
But our measurement actually says that the total density is approximately unity relative to the... Yeah, so it's not... The total of the dark matter, the dark energy, and the ordinary matter is unity.
Thank you.
So we have to conclude. We're out of time. So thank you very much. Thank you.